All right, folks, welcome to 8.7, where we're going to talk about indeterminate forms and L'Hopital's rule. First of all, folks, let's remind you how to evaluate a limit. And remember, the most easiest way to evaluate any limit is to simply plug in the value that we're evaluating the limit to. So in this case, the limit as x approaches -1. So we're going to take a look at the equation and plug the value of -1 into it. Now, something interesting happens here when I do that math. I actually end up with 0 over 0. All right, well, no big deal. We know how to work around that. In order to work around that, all we have to do is to simplify our expression. So that usually involves some factoring of some things out. So we'll factor out the top, and then, oh good, something cancels on the top and the bottom, and I'm allowed to evaluate my limit the old-fashioned way by plugging the value in now, and I end up with the answer of -4. Everything is all good here. Okay. Let's try one more, just to remind ourselves. Oh, man, okay, in this particular problem, I'm going to plug in the infinity. I'm going to see what happens as the top and the bottom gets bigger and bigger. And if I do that, I get infinity over infinity. The limit of that top actually ends up being infinity, and the limit of the bottom still going the same way. But that's okay, because one of the ways that I had to fix that was I was able to actually take the top and the bottom of this expression, multiply it by 1 over x squared over 1 over x squared, and again, evaluate that limit as x approaches infinity, and I get 3 minus 1 over x squared over 2 plus 1 over x squared. And if we remember, the value as x approaches -infinity of this little piece right here and this little piece here is both 0, so I end up with 3 over 2. If we look at this problem and look at the previous problem, what we're getting something here. We're getting a limit of infinity over infinity, or in the previous problem, we got 0 over 0. Both of these are what are called indeterminate forms. And when we get an indeterminate form, we have to fix the limit before we can do anything with it. Let's take a look at this problem. In this problem, we have the limit as x approaches 0 of e to the 2x minus 1 over x. So that's here. Let's see what happens when I plug in 0, because I should always do that first, just to see what happens. Let's see, that gives me e to the 0 minus 1 over 0. I get 0 over 0. Well, that is an indeterminate form. But here's my problem. I'm not sure how to fix this equation. It's not like I can factor the top. Actually, you can if you look at it close. But it's not going to help me simplify this expression at all. So instead, let's take a look at the graph and let's look at a table of values for this function. So here's what e to the 2x minus 1 over x looks like. And if we look at it, if we look at my table of values, as I get closer and closer to 0 from both sides, it looks like it's going towards 2. The same thing can be seen here on my table. Look there, it's almost like there should be a value right there at 2, but it's not. There is, in fact, a hole in my graph, but the limit still exists here. Well, that must mean that there's a way that we can actually calculate this. And the way we calculate this is using something called L'Hopital's rule. L'Hopital's rule says that if a function is in an indeterminate form, I'm going to summarize this whole thing. If a function is in an indeterminate form, and those indeterminate forms are listed here, you're either going to get 0 over 0, you're going to get infinity over infinity, you could get -infinity over infinity, or infinity over -infinity. It's one of those things. These are indeterminate forms. And if my function is in an indeterminate form, then the limit of those two functions is exactly the same as taking the limit of the derivative of the top over the derivative of the bottom. Please, folks, it is not the quotient rule. We are simply taking the derivative of the top and looking at the rate of change of the top and the rate of change of the bottom. If you think about it, what we're looking at is we're looking at the slopes of these tangent lines, and they're going to be exactly the same at both of those spots as well. Let's take a look how it looks with this problem. Again, we already did the math, and we know when we did this the first time, we got 0 over 0. That's an indeterminate form. So what I do is I go down here, and I make a little note to myself that, hey, I'm about to apply L'Hopital's rule. Especially for the AP exam, the readers like to see that. So we'll take the derivative of e to the 2x minus 1. Well, the derivative of e to the 2x minus 1 is 2 e to the 2x, that's the derivative of the top, and on the bottom, I get 1. Now we should be able to evaluate this limit just like we have before, where we take the 0 and we plug it into our expression. So I get 2 times e to the 2 times 0 power. Well, that's 2 times e to the 0, which is the same as 2 times 1, and I end up with my answer of 2. Just like I saw on the graph, everything worked out. Let's go through a couple more. So here, 2e to the 3x minus 2 over x, and we're evaluating the limit as x approaches 0. When I plug this in, I actually end up getting 0 over 0. You could probably see that. So then we're going to apply L'Hopital's rule. And let's see here, that will get me the limit as x approaches 0 of 6e to the 3x over 1, which I can easily plug in 0 into that expression and evaluate that limit now. I end up with the answer of 6. What about this one? The limit as x approaches 0 from the left-hand side of e to the x minus 1 over x to the third. Well, let's see here. If I just plug in 0 right away, let's see here, e to the 0 minus 1 over 0 to the third, I end up with 0 over 0. Okay, let's apply L'Hopital's rule. In this instance, it doesn't matter whether I'm evaluating from the left or to the right, I still get 0 over 0. I'll apply L'Hopital's rule, and I'll get 3x squared. But wait just a second. When I plug in 0 in this instance, I get 0 over 0 again. Oh no, what do I do? No worries, you can apply L'Hopital's rule again. So we'll look at the limit as x approaches 0 from the left-hand side, take the derivative of the top, over 6x. I get 1 over 0. Now, this is not an indeterminate form. This is not something that we can do anything with L'Hopital's rule. So now I have to think and actually think about what the graph of e to the x over 6dx is going to look like. And if I look at it from the left-hand side, this, in fact, will approach negative infinity. And if you think about it in terms of getting numbers, I think that that will make sense to you. All right, let's try another one. So this is the limit as x approaches infinity of x squared plus x over e to the x to the third power. Wow, okay. So let's here, I'll plug in infinity and see what happens. Well, on the top, that gives me infinity over infinity. So that's an indeterminate form, which means I'm going to do our favorite thing to do now, which is apply L'Hopital's rule. So I'm going to look at the limit as x approaches infinity of, let's see here, the derivative of the top is 2x plus 1. The derivative of the bottom, let's see here. Well, the derivative of e to the bob is e to the bob times d bob, which is 3x squared. All right. So let's see here. Well, okay, I get infinity over infinity again, which means I apply L'Hopital's rule again. So the limit as x approaches infinity, let's see here, on the top I get 2. And on the bottom, oh gross, I got the product rule. So let's see here. Well, we have the first, which is e to the x to the third power, times the derivative of the second, which is 6x, plus the second times the derivative of the first, which is like exactly the same thing I came up in the original problem. Okay, well, at least this one's easier to do because I know whether I simplify down all that stuff on the bottom, I'm going to get infinity on the bottom, but 2 is going to stay on the top, which means the bottom is getting bigger than the top is, and if that happens, I know the limit is equal to 0. Okay, now let's do some trig problems. I think the important thing and why I put this one here is because you want to make sure that you always check by plugging your value in for the limit first. Because if you don't, like if I wouldn't try this, at least informally in my head, I might actually try and use L'Hopital's rule and get something that's wrong. But when I plug this in right off the bat, I'll end up with the answer of 1, and there's not really any work to do. So be really careful of that. All right, what about this guy? The limit as x approaches 0 of x squared times the cosecant of x. Well, I'll plug in 0. Let's see here, 0. But if I remember what the cosecant of x graph looks like, the graph of cosecant looks like this. So if I look at this, the limit as x approaches 0 from the left-hand side, I'm ending up going towards negative infinity. So I actually have 0 times negative infinity. Now that's weird. But this is another kind of other indeterminate form, and we can't use this one to use L'Hopital's rule. But what we can do is we can take that expression and we can rewrite this as x squared over the sine of x. And when I write it like that, I do in fact get 0 over 0, which is an indeterminate form. So now I am allowed to apply L'Hopital's rule. So I look at the limit as x approaches 0 from the left of 2x over the derivative of sine is cosine. And now when I plug in those values, I get 2 times 0 over 1, which is 0. Okay, one more. Let's see here. So again, we'll plug in x. The limit as x approaches infinity of x times the sine of 1 over x. We'll plug in infinity. And that will give me infinity times, well, let me think about this. X is going towards infinity, which means I have 1 over a number that's getting, so this right here, this 1 over x is getting closer and closer to 0. So this ends up being actually the sine of 0, which I know is 0. So there's my other indeterminate form, infinity times 0. But that is actually no good, and we can't use that form, that indeterminate form, to apply L'Hopital's rule. So here's what I'm going to do. I'm going to rewrite this, and I'm going to keep it as the sine of 1 over x, and I'm going to write that times x as dividing by that reciprocal of it. Now that's kind of weird, right? But if I do it this way, this actually gets me the indeterminate form of 0 over 0. And now I can, in fact, apply L'Hopital's rule. Now, probably instead of thinking about this problem in the format that I've written it, probably what I'll do instead is I'll think of this as the sine of x to the negative first over x to the negative first. I just think that might be a little bit easier when I go to take the derivative of those functions. So that's here. So it's a limit as x approaches infinity of the derivative of the sine of Bob is the cosine of Bob times d Bob. Let's see here. That's negative 1 times x to the negative second power over, and then the derivative of the bottom, negative 1x to the negative second power. Hey, I can actually apply some algebra here. Check it out. Those will cancel out. So I'm left with the limit as x approaches infinity of the cosine of 1 over x. And if you think about that again, what's happening as this is getting closer and closer to infinity, right? The 1 over x becomes 0. So I really have the cosine of 0. So this is exactly equal to the cosine of 0, which is 1. All right, folks, that's all I have. Check out the homework problems for you to complete. If you have any questions, let me know.